Good afternoon to all of you. In the last class, we started with current sources. So we'll quickly go through what we did in the last class, and then further see some advanced current sources today. Okay. This was an Nmos current mirror where we had an I reference. This is one I reference which is generated by a band gaps circuit which would be stable with respect to VDD and temperature. So I would require I can use this one I references to power or to bias various circuits in our chip. So I can generate various biasing currents, I out 1, I out 2, I out 3, and they need not be I reference, they can be multiples of I reference by appropriately sizing the transistors. Okay, since the VGS is same everywhere, okay, we connect like this, so all the VGS is same. So the current can be altered by changing the W by N ratios. Okay, so W by N N divided by W by L R into I reference will be the I out, where W by L R refers to this size of this transistor, and W by L represents the MOS transistor, NMOS transistor, from where we are syncing the current. So is this okay with all of you?
Sir, I have one question. See that I reference we are giving at the initial, right?
Yes.
I'm just having a curious to know why will the current not drop while it goes through different transistors, I out 1, out 2, out 3.
No, where is this current going from? There is no gate currents, right? Gate is there will no current flowing into the gate of these transistors, right? So this current is I reference will
so
flow only.
How it flows basically? It flows through the gate, right? The gate of M1.
No.
Gate of M1, M2.
No, gate is open, right? It only provides the voltage to each of the gates.
Okay. So this provides the VGS basically to M1, yes. M2, M3.
Yes.
Okay, because because of that VDD at each of the I out 1, out 2, then that it creates a biasing basically.
Correct. Okay. So similarly, I can have these are known as sinking currents. I can have sourcing currents also. So I can have from VDD, I can have these transistors connected, but they will give a constant current. So that constant value of that constant current required for biasing can be set by using an PMOS and an I references. So earlier was a sinking current. This is a sourcing current. Okay. Again here. Between the this is the source for a PMOS, right, VDD, and this is the gate. So SG is same for all these transistors. If SG is fixed, then the current ratio will be decided by the W by L ratios with respect to the reference transistor. Okay, so I can get different I outs. So this we saw last time. And then we also saw that with one I reference I can have multiple sinking currents and multiple sourcing currents. Okay, it all depends on the W by L ratio. So once I generate one reference current, then I can generate all these sinking and sourcing currents up to the required value for different VLSI circuits. So there could be some 50, 100 circuits, and for each of them we can use these connections and get the required bias currents. The bias currents need not be same in each of the branch. We can set to the desired value by appropriately selecting the W by N ratios. Okay, is it okay till here?
Sir, one doubt.
Yeah.
Sir, if you are stacking this transistor like M1, M3, so I want to know the body connection of M1 should be connected with the VDD, yes. Or like for example, if the above one is the Nmos, okay, then if it's stacked, then its body should be connected to the ground, or it should be connected to the source.
No, for
connection.
All PMOS it will be connected to VDD. For all Nmos it will be connected to the ground.
Okay. Can we connect, sir, to source also? like for NMOS I am talking, like if we want to make a current source, in assignment we have to like in Cascode. So for example, if you are connecting this body terminal of NMOS to the source terminal, then it will affect BGS because substrate bias voltage is 0. But if we connect it to ground, then there is a difference between source and body. Then our BGS will increase. So it is dependent on us where we have to connect.
No, try to connect it on the ground only. Okay.
Okay. So is it wrong if we connect it to the source or anything if we do it?
No, I told you what is the problem on the schematic level you may not find, but when we are doing the layout, I told right those all the substrates will be connected to the ground, right, and if there is a voltage available on your source, right, and it is connected to the body, so you might get a 0 there.
Okay.
From the layout point of view. Okay, so we should avoid that.
Oh, okay, sir.
Okay. Then we saw one of a simple method of generating I references by using an resistance out here. So in this case, if I write the equation, I will find an I references VDD minus VTN by R. So you can get a stable I reference by using just an VDD and a resistance. Although this is not a perfect way of doing it, we will learn about band gap references later on, but I just introduce you to this circuit in the last class. So this is one of the methods of generating I reference I told, right. Then we saw right, it's an ideal if you just make a mirror like this. So if you consider the channel length modulation, then if VDS1 is not equal to VDS2, okay, which will usually be the case, then there will be a difference between the I1 from the desired value. Okay, so that introduces a systematic error. Okay, and there is another error, which is a random error. That is because while fabricating, M1 and M2 may not get fabricated exactly the same. Okay, so this is a systematic error, and there could be one random error also. So these are the two kind of errors which can be anticipated in these kind of circuit.
Sir, one question. What is the main reason this VDS1 not equal to VDS2?
Because VDS1 is fixed, whereas VDS2 comes from the circuit where we are going to employ this Baising, right? So that we don't have any control over that, right?
Okay.
So that is the reason. Okay. So to avoid mismatches, we said we can use these kind of. This is the this transistor, and M2 is spread on both the sides. Okay. Now here, if you see here, this is multi-finger, which we discussed in the morning. Even if this is one transistor, okay, M1 is one transistor, generally we keep W by L very, very large. If you keep for a same current, for a given current, if W by L is very large, I can keep VOV less, right? Isn't it? Right, for a given ID, right, if I is W by L and VOV, right. So if I keep W by L large, okay, VOV will come down, and we want VOV less, right, because it gives the headroom, right. We want VOV will be here, so we don't want a high VOV because that will affect the other circuits, right. So headroom will consume headroom, so we want to keep V. So I want to keep very large W by L. So large W by L, generally per finger the width is limited by the technology. Okay, it will be some say 50 micro per finger. So if you have to make a transistor with say 500 a micro, then I will have to use 10 fingers and interconnect all the gates and the drains and the source. Okay, so generally you will have now for these kind of current sources, you will have multi fingers which are connected in parallel. Is this okay with all of you? Right, and since we space some portion or some fingers here, okay, for the mirror and the reference fingers out here, then whatever is the along this axis, if there is a process variation, and that gets compensated. Similarly, we discussed here these are the other configurations where you have the references placed here and the mirror fingers which are placed here. So today morning in the VLSI class we discussed these fingers, right?
Sir, I have one question. So you are saying M1, so this common centroid design, this is used to reduce the process variation, right? Which is nothing but M1 not equal to M2.
Correct.
Right. So the M1 not equal to M2 means we are considering size there.
Yeah, width.
What not equal means width is not equal, you are saying?
Not only width, process variations means oxide thickness, and what it could be any. Like for example, here if you see here, this oxide thickness is 5. Here it is 6. Here it is 7. It is 8.
Okay, this variation you are saying. This is process variation.
Yeah, these are all process variations. Okay.
But how arranging this in them in this way? How will it reduce the variation?
See, 6 plus 7, okay, this average is 6.5, right? And this is a 5 plus 8, again the average will come out to be 6.5, right?
But how will we know? But the variation can be random, right? It may not.
No, generally when
average may not be
generally
exactly
when you do a process in a chip towards the edge, okay, there will be some process and variation in some particular direction only, right? It will not be random variations. Generally during fabrication that can happen. That not to the center of the chip, only towards the corners you will find there is some variation which is happening.
But however, in the next slide, you are arranging it alternatively, right?
Yeah, this is this is for both directions, like plus and minus directions. So if there is a process variation like this or process.
So if you are taking an average, you are saying.
Yeah,
okay,
just taking
an average, that will even out.
Yes, correct. Okay.
Sir, one doubt.
Yeah.
Sir, you mentioned if we increase W by L, our VOV requirement will decrease.
Yes.
So I didn't get that thing.
Because for a given current, okay, I is given by is proportional to W by L and VOV square, right?
Correct.
So when I am all I am trying to do is bias a circuit with a certain bias voltage I, right? So if I increase W by L for that specific current, then VOV requirement is lesser, right?
Okay, in order to get the same current.
Yeah.
Okay.
Then we saw in this particular circuit there is one systematic error because the VDS is not equal and that error is I out minus I out ideal by I out. If you do that, you will get lambda into V out minus V out, right? And so this is V in and this is V out. They need not be the same. Okay, so you will have some error which is there. Now also in the small signal analysis, when you look from the top, I will have an R0 here. Okay, so in the small signal analysis, if you see here, this is providing R0. Output resistance of this is R0. So these are the two issues with this particular design. Then we thought of an improved design where we connected like this. Okay, when you do like this, there are two distinct advantages here. Okay, one advantage is now when you are looking from the top, okay, this derivation we did in the last class, so I'm not going to repeat it. So it is GM4 R0 square. Okay, so you see a huge impedance. So when a small signal is applied on top out here, okay, so lesser small signal current will flow here because it is a much bigger resistance here. Okay, it is square into GM. So you can see it's a huge gain in the resistance has gone up by several orders. Okay, so that is the reason we can use this particular circuit. Okay, so if somebody remembers from the previous class, okay, what is the disadvantage of this circuit?
lesser headroom.
Yeah, lesser headroom. Okay. There is one more advantage which I didn't discuss last time. Okay. See, the voltage here will be VT plus VOV, right? Because this is the VGS. VGS has to cater for this current and the threshold voltage. So this is VT plus VOV. Is this okay with all of you? Is it okay? VT plus VOV, the voltage at this node. Yes, the voltage at VB will be, what about this gate to source voltage? It will be again VT plus VOV. So the voltage at VB will be 2 VT plus VOV. Okay, this voltage will be 2 VT plus VOV. Is it okay till here? Now if you see, if I come back here, okay, across this there will be 1 VT plus VOV. Okay, so this will again, Y is also now VT plus VOV, right? X is also VT plus VOV, right? So there is no systematic error here. That means now I reference, right, is a multiple of or other way around, I can say I out is K times I reference, where K is an fraction ratio of W by L of these two transistors. So there is no systematic error here. Is it okay with all of you?
Sir, earlier you said systematic error is because VDS is not in our control.
Correct.
VDS2.
Correct.
So how we are controlling it?
Here this VDS is in our control, right? This VDS is in our control, right?
Which VDS?
Y.
The Y. How? Okay, I'm unable to understand. Can you please
VT plus
explain,
VOV. This is VT plus VOV. Correct. This node is VT plus VOV. 2 VT plus VOV. If I come back here from here to here, gate to source voltage required here will be VT plus VOV. So if I from 2 VT plus VOV, if I remove 1 VT plus VOV, I will get back VT plus VOV. So now VY and VX are same.
Why we will remove 1 VT plus VOV?
Because if that is the current which is from here to gate to source voltage is VT plus VOV, right?
Oh, we are using that. You are saying, okay, we are okay.
Right? So you get, right? Now from here to here, but if you see here, I have to reduce 1 VT, okay, for this to remain in saturation. So that is the condition for saturation. So here the minimum voltage which is required here will be 1 VT from 2 VT plus VOV. If I remove 1 VT, it will be VT plus 2 VOV. So this is the drawback of this circuit. Okay. So this has got two advantages. One, the resistance, the small signal resistance is R out is much higher. Second, there is no systematic error. Okay, that is two advantages. The disadvantages is VT plus VOV is the minimum voltage which is required here. Is it okay with all of you till here?
Sir, can you explain once again this M3, how M3 gate voltage is 2 VT plus VOV?
Yes. See, this is VT plus VOV, right? Okay. Now this same current is flowing in M3 also, right? So I is flowing. So what will be VGS? VGS will be VT plus V overdrive, right? For the same current, right?
Right? Yeah, right, sir.
Okay, because for the same current.
Okay, so X
W
node
by
is
L is
VT
same.
plus VOV.
Pardon?
At X node it's VT plus VOV. So in order to cater this, we need 2 times.
Yes.
So if we subtract, it will be finally VT plus VOV.
Correct.
Okay.
See, 2 times is one for VX, one for VY. So that's why it becomes 2 times.
Yes, one for M1 and one for M3. Yes.
Yeah.
Yes, tell me.
Sir, VD for M4 will be 2 VT plus VOV, no? VD for M4 will be 2 VT plus VOV.
No, now we are talking
M4,
about
sir.
the minimum voltage required for M4 to remain in saturation. So for that, for M4 to remain in saturation, for the end of the saturation, from the gate voltage, gate to source has to come to VT. That is the minimum voltage. So I have to reduce 1 VT with respect to the gate voltage to find out what is the minimum voltage required here. Is it okay? So it is 2 VT plus VOV, and I remove one more VT. Okay, so that is the minimum voltage which is required here for this to be in saturation. So from 2 VT plus VOV, I remove 1 VT, so 1 VT will remain and 2 VOV will remain. Is it okay? Yeah.
Yes, sir.
Now, then we saw one more. You can have, instead of one, you can have a triple like this. So if you have a triple like this, then the output resistance will go further high. Okay, it is R0 cube. Here it was R0 square. Right, now it will go up to R0 cube. Okay, now again this also doesn't have any systematic error, but it will require much larger headroom now. Okay, if you try to compute the headroom, you will come to know that it will require I think from here to here it will be 3 VT, okay, plus VOV, and then 1 VT can be removed here. So this will finally come out to be 2 VT plus 3 VOV. Okay, that much of headroom will be required. So this is again a circuit which is which is very high resistance, but for certain applications where you don't have headroom, then this may not be recommended. Okay, so this is known as triple cascade.
Sir, where is that 1 VT going in the previous one?
From
3
here,
VOE?
From here to here, 1 VT will be required for this to remain in saturation.
Okay.
Now here, right? So this voltage was 2 VT plus VT. Suppose I introduce a 1 VT here, drop somehow. If I introduce 1 VT drop here, okay, this will be 2 VT plus VOV, 1 VT drop here and another VT drop here. Then this will be merely 2 VOV, and VOV is generally around 0.1 to 0.2 or maximum up to 0.3, 0.4. So this will be much better. So I have to somehow drop one more on a VT in between. Okay, so that is known as low voltage cascode current source. Okay, so that is low voltage. Low voltage means lower headroom for much better headroom for the next circuit. Okay, so we have to somehow reduce this output voltage requirement for this to be in saturation. So we are going to drop one more VT in between. So how to drop that 1 VT? See, this is the circuit which will drop 1 VT. Okay, now if you see here, what is happening here? This is VT plus VOV. Okay, and this ratio is, right, this W by 3 is 1/4 of W by L. Okay, so what will be the overdrive voltage required here? It will be VOV or more than VOV. See, W by L, okay, is 1/4, right? So VOV has to be twice, right?
More than VOV.
Right? Because in the ID equation, W by 4 is 1/4. So VOD has to be, V overdrive has to be twice. So from here to here, okay, it will be 2 VOH. Right? The overdrive voltage for this transistor is 2 VOV. Okay, in the textbook it's written VOD. I have used VOV, so don't confuse that. VOV is nothing but VOV only. Okay, so overdrive. Okay, overdrive is some many books it's written OV and OD. So both are one and the same. Okay, so here it is VT plus VOV. Here it will be VT plus 2 VOV. So this VGS is VT plus 2 times VOV, because the width is 1/4. Okay, length being the same. Okay, and hence this voltage has come to be VD plus 3 VOV. Okay, is this okay with all of you? Anybody has got any doubts? Yeah, is it okay?
Can you please repeat one?
Yeah. What is the voltage here at Vx, VT plus VOV? Is this much okay?
Yes, sir.
So because this is an VGS will be VT plus the threshold voltage plus the VOV. VOV corresponds to that current. So for that current, how much overdrive voltage is required, right? So this is VT. Now here to here VGS, okay, will be again VT plus V overdrive. So what is the overdrive voltage out here? Since the W by L is 1/4, so V overdrive has to be, because this is square here, twice the overdrive voltage will be required here, right, for the same current. Right, the currents are same. It is flowing. The same current is flowing here. M3 and M1, the same current is flowing, and that is why more overdrive voltage will be required here, because the width is only 1/4. So more overdrive voltage. But since there is a square here, for 1/4 reduction, I just require double the size, double the overdrive voltage. So and hence VT plus OV, and here it is VT plus 2 VOV. So the total requirement voltage out here will be VT plus 3 VOD. Is it okay?
Yes, sir. Thank you, sir.
Okay. Now coming from here to here, I can remove one VT plus VOV, because this also requires VT plus VOV.
Sir, I have one doubt. What is this VOD? VOV is overdrive voltage, right?
Right. VOD is also same. Okay. VOV and VOD are the same. Different notations. I took it up from a different textbook, so that's why it's written VOD. Okay. Okay. So coming from the gate to the source, I can remove one VT plus one VOD. So this will become VT plus 2 VOD. Is it okay? How?
Yes, sir.
Sir, this is where you are saying at M5, right?
At M5. Right? Now from here to here, I can remove one more VT. So this will come out to be 2 VOV. Right? So now if you see here, the total requirement is much lesser, right? VT is very, very large, right? If you see for 180 nanometer, it is around 0.6, right? So initially we saw the requirement is here, right? 2 VOT, TVT, 2 VT plus 3 VOV, and in the prior in this circuit we saw a VTH plus 2 VOV. So VTH is a very large value, 0.6, compared to VOV is very, very small. So in this particular circuit, the total minimum voltage is 2 VOV, which is much lesser. Okay, so there is an advantage. Is the advantage clear to all of you?
Yes, sir.
Okay. Now the resistance as seen here also is like in the previous case, it will be GM into R0 square, so high resistance. So that there is no issue with that, but there is an systematic error now in this particular circuit. Okay, what is the systematic error? Now if I try to find out an VY, okay, this is VT plus 2 VOD. If I come from here to here, another VT is to be removed. So this will be VT plus VOV will be removed. This will become VY plus VOD. This will become VY is equal to VOD. Is it okay with all of you?
So for M5, sir, if VGS3 is 2 VT plus 3 VOD, then sir, VDS, V overdrive for M5 will be VTH plus 2 VOD, yes, sir? How come that point is VTH plus 2 VOD?
Because 1 VT plus VOD will be required.
For
M5. M5 size will be same as that of M1 and M6. Only M3 size is different. So 1 VOV and 1 VT will get dropped across the gate to the source.
So if you drop one VT from VGS, then it will give V overdrive for
no,
M5
and one
VDS.
overdrive voltage also. Any gate source voltage to support the currents should have VT plus VOV also. Okay. So here,
yes,
so it will get 2. From here to here also, 1 VT plus 1 V overdrive will get dropped. So I have VY is equal to VOD, right? So now VY. What about VX? VX is VT plus VOV. So now we have introduced a systematic error, right? So this circuit has a problem of having systematic error, but the total voltage requirement here is lesser. Is it okay with all of you?
Sir, what systematic error we have introduced, sir?
Because
What is it actually?
here VDS is not same here for M1 and M2. So I can't say an I out and I reference. I can't define by that relation, right? By W by L ratios.
Okay.
Because VDS is different here. Okay. Okay, so this is an issue. Now we'll try to modify this circuit further so that these two voltages can be the one and the same. So let's try and do that. So now I give a different volt. Suppose I give a different voltage here, okay, in this circuit, which is VT plus VOV. Okay, if I do that, what happens? This is VT plus VOV, and from here to here, again, this is of the same size in this particular case. Okay. So I am not worried about the size out here. So this voltage will be VB will be this VB I am giving externally, VT plus 2 VOV, right?
Sir, pointer is very difficult to trace.
Okay. Yeah. Okay. See, from here to here it is VT plus VOV. Okay. So now I am giving this voltage out here. Okay, from here VB I am giving externally. Okay, VT plus 2 VOV. So at this point, at the output point, 1 VT will get dropped across this, right, for it to be in saturation. So it is 2 VOV, right? So that is okay. So it has got a lesser overdrive voltage. And if I consider the voltage at X, now here the drain and this is not connected. So for this to be saturation, the voltage between the drain and the source will be VOV. Isn't it? Why is X VOV? Because M1 is in saturation region, right? It's in the edge of the saturation where I can have VDS is equal to VOV. Is that aspect clear to all of you?
Yes, sir.
Huh? Right? This is V overdrive. Right? So that is the reason Vx is overdrive. For this to be saturation, it has to be overdrive voltage, right? So this is Vx. Now this I am giving Vt plus V overdrive. Again, coming from here to here, okay, another Vt plus VOV will be dropped across this gate to source. So I will get VOV. Now I have eliminated the, so in this particular circuit, I have eliminated the systematic error. At the same time, I am getting 2 VOV as the minimum output voltage which is required here. Only thing is, now I have to generate this VT plus 2 VAV externally. Is it okay with all of you? Doesn't matter.
Sir, can you please explain how VB became VT plus 2?
Sir.
Yeah. Yeah, let me take first Reshma's question. VB plus, this is how it has become. I am going to give this voltage from outside. How I am going to give, I am going to explain it in the next slide. Does that, if I am giving this, I will get this and this. Is it okay?
How this circuit works?
Yeah, one at a time.
Sir, how this circuit works?
How this circuit works? I am going to give a voltage VB here, which is equal to VT plus 2 VOV. I have not yet explained to you how to generate VT plus 2 VOV, which I will explain in the next slide. Okay. Now, time being, assume I have VT plus 2 VOV. If I have VT plus 2 VOV out here, right, from here to here, 1 VT will be dropped, right, for this transistor to be in saturation, just at the edge of saturation. So that VT will vanish. So 2 VOV. That means the headroom required here is very, very less. 2 VOV. Okay. Another advantage is it is VT plus 2 VOV. So from here to here, another VT plus VOV will be dropped. So the voltage at Y will be VOV. Right? And unlike in the previous case where there was a connection like this, now there is no connection like this, right? So this gate voltage is not available here. Now this is coming from here, from this point. So what will be the drain to source voltage? drain to source voltage will be in the edge of saturation, it will be VOV only, right? Right, that is the condition for saturation, right? VOV, VDS is equal to VGS, right, minus VT, right? So that is V overdrive. So that is the condition for saturation, right? This we learned. So here also it is VV. So there is no systematic error, as well as the output voltage requirement is low. Is this understood by all of you? Anybody has got any doubt? Let's clear these simple doubts and then move forward. Yes, tell me.
Sir, if you are applying VT plus 2 VOV at VB, then the voltage is of gate, that is VG is equal to VT plus 2 VOV.
Correct.
Right, sir?
Correct.
Sir, if you are then Y will be the source, the Y point will be the source point, sir?
Yes.
So if Y is VOV, sir, moving backwards, sir, then VGS will be VT plus VOV, VGS, voltage between gate and source, sir, VT plus VOV.
No. VGS, okay, minus VTN is known as the V overdrive.
It's equal to VDS. Oh, correct, sir.
Right? VGS minus VTN is known as the
Yes,
V
sir.
overdrive, or VGS is equal to VTN plus V overdrive. Right? So from here to here, there is one VTN and one overdrive. VTN is just required to switch on the transistor. VOV is required to sustain that current. Right? So it is VOV, and if you add VTN plus VOV, I will get a VT plus 2 VOV there. Is it okay with all of you?
Okay.
Yeah, Reshma, is it okay now?
Yes, sir, it is clear.
Okay. Now let's assume that this bias voltage is available with us. Now how to generate that voltage? So this is this is generating. So I have I reference out here, right? And I am keeping this voltage as 1/4 of W. Okay, in this particular case. Okay, so 1/4 of W if I keep, right, then it will become 2 VOV. Right, here this voltage requirement will be 2 VOV because the width is now here 1/4. So 2 VOV. So this voltage out here VGS will be VT plus 2 VOV. Simple, right? How to generate VT plus 2 VOV? So this is an additional circuit which will generate this voltage for me. Right? The same reference current, only with respect to M1, I am having one more bias transistor whose width I am keeping 1/4. So since I am keeping the width by 1/4, I will require twice the overdrive voltage. Okay, because right, there is a square out here. This width is coming back by 1/4. So overdrive voltage will increase by 2 times. So this is how I generate that bias voltage. Yeah.
And this voltage is generating because we are passing this high ref current, right?
Yeah, this by passing this high reference, yes.
But sir, in MOSFET, isn't it the reverse? Like if we apply VGS, then only I ref will flow.
No. See, for all these circuits, we have to first generate an I reference. Okay.
So I ref will automatically create a channel and it will develop this potential difference.
Yes.
And this is happening because we are assuming that I ref is an ideal current source and it will always supply the current.
Yes.
Okay.
Correct. Okay. So we will generate I reference. We'll see those circuits.
Sir, basically.
Yeah.
Sir, in this circuit, basically we are making the width 1/4. So VOV becomes will become 2 VOV.
Correct.
As per that ID formula.
Correct.
And as the source is down, so VGS will be VB.
Yes.
So VV minus VT is equal to 2 VOV, and VB becomes VT plus 2 VOV. Right?
Correct. Absolutely.
Yes.
Right? So this way also you can. This is another topology to generate an VT plus 2 VOV, right? So in your own time, just try to write down the voltages here and try to analyze. You will get the same voltage here by doing this also. right? So the entire explanation is given here. So I expect you to go through this and try to find out how VB is equal to VT plus 2 VOV in this case also, right? So that it is simple derivation. Everything is given here. You just have to try and understand this. So these are the methods which you generate VB. Now this circuit will start looking like this. So we have generated, right, this VB here. So that VB is connected here. Is it okay? This circuit. This was this circuit, and this was the second circuit to generate VB. So I have patched it up here. So now this is how the current will look like. Is it okay with all of you? Okay, now this circuit is very useful circuit. If you see here, okay, it doesn't have a systematic error, right? And it has got an very high output impedance when we're looking from here, and that is the second advantage. And the third advantage out here is the total requirement is just 2 VOV. Okay, so this circuit is very useful circuit which one could use for your circuits. Okay, so this has all the small issues which we faced in our earlier circuits, that has been eliminated here. Okay, this is again the circuit in which this generation of VB is done with it. Other circuit, this you need to analyze. Okay, so this is known as low voltage current source 2. Yeah, tell me.
Sorry, sir, one is no systematic error, the other is that minimum V out required is only 2 VOV. What was the third advantage, sir?
Third advantage is like the impedance as seen here will be GM into R0 square.
Okay.
Right? High impedance. Okay. Right? These are so this is one.
Sir, but this actually requires one more additional current source, right?
Yes, correct. So everything in analog circuit, okay, it is the same current. Not I reference will be generated. Suppose I have generated one I reference, I can use one PMOS to provide here. Again, I can take that again to one more PMOS. We learned, right, how we can.
Yes.
Okay, we can make so we can do that.
The initial current.
Right. So one in the whole VLSI circuit there will be only one V reference. With that I can have n number of branches. Okay, but obviously the penalty is a little bit of more area, more number of transistors, more power. So this VDD I reference power twice. So obviously the penalty is there. So nothing comes for free in either in digital or analog. There will always be some trade-offs between different figure of merits. Okay. Now we have these kind of mirrors also. This is slightly different. Not very. This is the one which is used in one of the best circuits. But you can have some slightly simpler ones out here also. But this is not. You will find that this is not as good as the other one. But we'll see. But it requires just 3 transistors. The configuration is slightly different, and it is known as Wilson out here. So this is VT plus VOV. So this is available here. VT plus. As you move from here to here, it will be 2 VT plus VOV, because one more VT plus VOV will be added out here. Okay, and from here to here, one VT will be removed. So obviously this will require a slightly more voltage out here, right? So this will be what 1 VT if you remove, it will be VT plus 2 VOV. So that much will be required. But it also has got systematic error also, because this is VT plus VOV, whereas this is just VOV. So it has gotten systematic error also. But the thing is, it is simple if you and it consumes less power. Okay. Now please understand one thing. We are telling all this VOV will be equal, but the currents here are not equal. Okay. Currents are equal because I have I reference equal to W by L and VOV square. Obviously there is a constant in between, and this current I out is W by L, different W by L, and VOV square. So these are constant, okay, but these are different, and W by L also will be different, okay. So between M1 and M2, okay, the overdrive voltages are same, because gate to source voltage is same, threshold voltage is same, so overdrive voltage also will be same, right? So these are same for these two transistors, but the currents are different. Currents are different because W by L's are different, okay. So this could be 10 times of the current which is flowing here, okay. Is this okay with all of you till here?
Hello.
Yeah, tell me.
Sir, it is similar to what we have done, I think a 2 or 3 circuit back.
Yes, it
Kind
is
of.
slightly similar. Instead of making a connection here, we are making a connection here.
Okay.
Right? It is slightly. So it is known as Wilson mirror. Right. So there is a modified Wilson current mirror also. Here we are giving a connection like this out here, right? So here you will find a VT plus VOV, and if I move from here to here, okay, for here to here it is VT plus VOV. From here to here it is again, so this will become a 2 VT plus VOV. From here to here, if I go here again, 1 VT will be removed, okay. So that will create an higher headroom requirement, but then this voltage, okay, and this voltage, so it has got a higher output resistance, but the minimum output voltage is this, right? So this is not desirable, but systematic error is 0 here in this particular case, right? Because from here to here and here to here, if I remove 1 VT plus VO, so from here it is 2 VT plus VOV. So these two gate voltages are same, okay. So from here to here 1 VT plus VOV will be dropped. Here to here also it will be dropped. The same thing will be dropped here. So you will find that so there is no systematic error, but then a minimum output voltage has gone high. So these are some of the other simpler, which requires lesser number of transistors, okay. So these things, but if you are actually working in an industry, I would suggest you could use this particular by having a little more of power, but this is a much stable circuit. So these are other two circuits which are there. Yeah, okay. So
Thank you, sir.
let's start now here. Now we learnt about all these current circuits. Basically we are generating all these reference voltages and all to bias circuits, correct? So now this is a simple CS amplifier where I need to give an bias voltage and I need to give an input signal. So I have I will give the bias signal out here, right? So how do I give a bias signal? So I give a reference voltage here, I can give MB here, I will generate out one here, and I give an RB here, so I will get the DC voltage out here, right? And then I give an AC signal, okay. So this is biasing a simple CS amplifier, okay. Can somebody think of a reason why this RB is required? Is it required?
To get the voltage output, sir.
No, see, there is no current flow here like this, right? So
for isolation.
Yeah,
between VDD and
if you can be a little more specific. See, if I don't put an RB, okay, there will be a gate capacitance, right? MB will give a gate capacitance. This is also a capacitance. So those two capacitance, this capacitance, this transistor can be a large transistor also, right? So because we said this has to be large, W by L is generally kept large. So that large capacitance, if I put it here, will it affect my high frequency? It will affect, right? When I give a high frequency signal, it will if this RB is not there and I have a large capacitance here, okay, so that will that will reduce my gain. So that is the reason I put one large resistance in between here, and no current flows here. this potential will be available. Since no current is flowing here, it's a large resistance. This voltage will be available here for DC biasing. Is it okay with all of you? The purpose of RB is clear? Okay.
What is the range of RB?
Yeah, tell me.
What is the range of such?
RB could be in a few hundreds of kilo ohms. Okay, you can do that. Right? Okay.
So can I repeat why we are using RB?
If you don't use RB, this MB transistor, okay, the biasing transistor is generally we keep W very large, okay, so that if you keep W very large out here, you will find this is adding a direct capacitance at this node, right, which could affect your high frequency operations, because that capacitance will short circuit your high frequencies. So at high frequencies, and I don't want signal to be attenuated, so I will keep an RB in between. Is it okay?
Okay, sir.
So these are some of the variations. Okay, that RB resistance can be implemented by Nmos transistor only. Okay, so RB is nothing but, if you see here, the gate is fixed here, gate voltage is fixed here. So if you see here, this is the channel resistance, which could be in saturation region, it could be R0, very high value. So you can fix this, you can again make it, because this is fixed voltage out here. So that fixed voltage again can be generated like this. Okay, so generally when we see in the layouts, the resistances they consume lot of space in the layout, and they are noisy also. So instead of having a pure resistance, I can use these kind of circuits which is equivalent to a resistance here. Okay, constant gate voltage is applied here. So this is a constant current source. So if I look from here to here, it is R0. So that kind of high resistance. So instead of here, this resistance has been replaced by this combination of these two transistors, putting a high resistance here. Okay, so these kind of things we can do.
Sir, can we go back to the previous slide? One more slide.
Yes.
Why we are giving one more one more connection to the gate actually?
Here?
Yeah, Vin is a bias, some voltage which we consider as a bias.
Which Vin?
Yeah,
Vin
this
is
is
an
a
AC
Vin.
signal, right? Vin is the AC signal which is coming here. This is that resistance network we have, right? So instead of that, we are giving a constant bias, a much better bias signal.
Okay, it means that whatever you have giving down is like a kind of DC signal.
Yes.
The Vin is AC, right?
Correct. Vin is AC signal.
So generally, in a practical design, which signal would 2 it won't be there, right? Only 1 will be there.
2 will not be there means?
If you see the practical design, gate will have only 1 connection.
Yes.
So how we are going to separate this like a representation in a reality?
No, as such, when we made an when we made an CS amplifier, if you remember, we had put R1 and R2, right?
Yes.
Okay, so this is but when we also learnt, when we make R1 and R2, there won't be any bias stability. Then we introduced one more resistance in the source side, and then we saw that gain is deteriorating. Then we put one capacitor. Okay, so instead of doing all that thing, okay, so instead of one resistance here and a bypass capacitance, I remove all those things. Now I have a standard reference signal out here. Okay, so I am giving a good biasing voltage here. So there is a bias stability also. Is it okay, Vishwanath?
Okay. Yes.
Correct?
Yes.
Okay, so this is
But
stable
I see a lot of circuits, we don't even use this biasing concept.
This biasing concept, is it?
Yes, come in a completely. We just get the input signal. Okay, that will have a bias directly DC. What I mean, we don't use resistor divided concept or this extra circuit here for the gate.
No,
I haven't seen this much, designs.
No, but the input signal, whatever is coming, right? if it has got an inbuilt DC component to bias your voltage, okay, still I won't consider that because unless if that DC voltage is not stable, it will change the DC voltage will change the DC currents, and that will in turn change the gain, and that will set in non-linearity issues. So even if the input signal has got some DC component inbuilt, unless that if that DC voltage is stable, it is okay. If it is not stable, I would want to isolate that DC component and take only the AC component and give separate DC signal. This is what is the recommended.
Usually DC signals will be stable, right?
No, it depends from where it is coming, right? That signal. If you have an inbuilt DC which is stable, then it is okay. You can do that.
Okay, consider example, we are generating VIN from the current measure. Okay, some kind of reference voltage.
Yes.
Or it is from the band gap output. These are the stable outputs.
Yeah,
right?
Stable outputs you don't require. You can do that.
Yeah, I was wondering, like, okay, because majority circuits DC should be stable, but still we are using this kind of circuit.
Majority signals. What are your analog signals coming from? Where it could be a video signal which is coming, it could be an audio signal coming, right, from the external world.
It means that when it is coming from the external, right?
Yes.
Okay.
Correct. So all those signals need to be filtered out. Those DC components.
Okay, especially this RC is acting like a kind of filters, right?
Yes.
Okay.
Okay.
Thank you.
So this is okay. Now this I have. Okay. This is between two stages. This is one stage. This is the second stage. Okay. So when I'm coupling from one stage to other stage, okay, if I design it properly, I don't have to create a biasing for this. Okay. So here now suppose this is biased already with some current source, okay, and then hence this DC operating point is stable. In that case, I can directly couple it here. Okay, does that answer your question, Vishwanath? Okay, so you can do that kind of. So this has to be stable. So if it is stable, then we can do these kind of direct coupling also.
Yes, usually internal our architecture we will see only this kind of thing. We don't add extra legs because it is unnecessary.
I'll tell you there will be a lot of, if you see IC 741 circuits and all, because the DC voltage this particular stage, okay, suppose the requirement is such that this operation voltage is 1.1 or 1.2 DC operating point. Here it is say 1.8. Here it is 1 point somewhere in mid, okay, 0.9. Whereas suppose the requirement out here is only say 0.7 volt. Okay, there will be mismatch between these two DC voltages, right? So it depends. When you are making a large circuit, each of the branch, the biasing requirement may not be the same, right? Because this might be a different. The requirement of here might be to drive a low load, so you might want to bias this at a different. So it depends. So we can't say universally we can do that, depending on the requirement. So each stage will be designed separately, and if you can match the DC requirement, it is good. If you cannot match the DC requirement, then you will put a blocking capacitor here and put an biasing circuit out here. Is it okay?
Yes.
Yeah.
Thank you.
Okay. So this is for an again biasing circuit. Here on the top, instead of load resistance, okay, I put a constant current source. So this is one, right? So now what will be the gain of this circuit? It will be GM1 into the resistance here is, this is a constant current source, right? So it will be R02 parallel to R01, correct? So instead of RD, instead of GMRD, it will be GM1 into R01 parallel to R02 in this particular circuit. So now this also, since if I have a reference current, So I can use a current mirror here like this. Okay, so this is the biasing at the gate, this is the biasing at the top. Is it okay? Is this circuit understood by all of you? What we have done, right?
Sir, but here also that resistor will be replaced by the MOS, right?
Here also, yeah, you can replace this resistance with a MOS, right? So this is gate biasing. Here this is the current source I am using as a constant current source on top, right? So the net resistance as seen to the top will be R02, so which will be in few very big kilo ohms, and seeing in the bottom also will be, so they will be parallel. So this particular circuit will give you much higher gain as compared to RD, okay? And this particular configuration, it will be easy to get the operating point somewhere in between VDD by 2 also, okay? Because you see, you just have to size these transistors so as to get a proper operating point also, right? So these are the kind of biasing things which we can do, right? And for the common gate, again here we are applying the input signal here. Here we need to give a biasing signal, so we are generating this voltage out here. So for the common gate voltage, if I have to generate more voltage than VGS in that case, so I have put one more RB here. So now if you see here, it will be VGS plus this voltage also, so I can get an higher voltage out here. So whenever I require more voltage, like for example, for a common gate, I require higher biasing voltages, so I can use like these circuits to generate that higher voltage, right? Now here I have used an RS. I can use one constant current source also to bias this, okay? So this is a constant current source instead of RS. Now I have used a constant current source here, right? Here on this biasing voltage is also generated by this source, and also the current source is also used. So these are the various kinds of biasing networks with the current source. We have learnt about current sources. Now using these are the applications of all these current sources here. How to bias an CG state. Okay, is it clear to all of you? Anybody has got any doubts in these circuits? Okay, so we learnt about CG, right? So this is how the biasing is done, and this is like for the this is for the source follower. Source follower is nothing but the CD amplifier, right? Where you give V in and you are taking the V out. So I have to bias this. Okay, if I have to bias this, so I can give a constant current source here on here, right? So that it gets biased. And also I need to provide some DC voltage out here. So in this case I can just put one resistance here. So this current will be current which is flowing here will be decided by M2, the current. So I can bias, but I require an DC voltage here for this to be in operation. So I can give an R in here. So this is a constant current biasing for a source follower. So this kind of biasings are.
Sir, how are in providing the biasing voltage for M1?
See, the current is restricted by M2. Okay, so this is a constant current source, but this voltage has to be more than VOV plus VT. So by putting a resistance out here, I can get the required voltage out here.
Then gate voltage is directly at the VDD?
Yeah, there is a resistance, a high resistance which you need to put in here.
But we are biasing this M1 at VDD.
Yes.
Sir, any reason for that? Normally, VG is not that high.
No, you can put in you can put in a slightly lower VDD also by using an resistance, but this also will suffice actually.
Okay, so is there any particular reason why we are biasing this at VDD, or
it has to be as close as VDD, so that you get maximum. This voltage has to be right from this voltage for maximum output voltage swing conditions. Okay. So if you keep it as close to VDD, an input signal out here, right?
So gain of the source follower is I think GM RS by 1 plus GM RS.
Yes, you have to keep GM very very high to get an unity gain out here. Close to unity.
If we increase this gate voltage to VDD, how this will help the cause?
Okay. GM will be this is an Nmos out here, so 2ID by VOV. So I need to keep the overdrive voltage
small.
Small.
Yes.
Correct. Okay. So but the current is fixed out here. Okay. The current is already fixed by M2.
Yes.
Right.
So only thing we can change is this gate voltage.
Yes.
And that has to be very small. I mean greater than BT, but somewhat 100 to 200 millivolt more than BT.
No, I think the W by L has to be very large out here to get a higher G. Okay, we'll discuss this in the next class. Okay, let me analyze. Okay, what is the issue out here? Okay, so this is a source for our Baising. Okay, so with this we come to an end of half the course. So you will have a mid-sem exam based on things which have been discussed till now. So before that, let me show you some simulation results also. Okay. Now this is a common source amplifier, right? So I have this current which is flowing here. This is the reference current 20 micro, right? So I am biasing this this transistor with some currents, and also I am generating from here I am generating VGS to be given here. Okay, now if I see here, this is 10 micro. Okay, this current is 10 micro. So what would is the, this is 100 micro. So what is the current which is expected to flow in this branch? Anybody?
10 times.
Yeah,
10 times.
10 times. And this is also 100 micro. So the current which is expected to flow here is also 10 times. So let me run the simulation. So let me plot this current first. So it is around 220, right? 220 instead of 10 20 200 I am getting a slightly higher current. Now if I try to plot the current out here, okay, let me change the mouse size, otherwise it will create. Okay, so if I try to plot the current here, okay, this is also right. This current is an AC signal out here, but centered around 200. So it is going up to 221 micro and 219 micro, right? So this current is varying current, right? This is fixed current 200. This is a varying current, right? Because I have given an AC signal. Is this graph okay with all of you? I am getting an if I plot this current, it will be 20 only, right? See, this is 20, whereas the currents there are 200, around 10 times. It is slightly more than 10, okay, because of the other channel effects, and we saw that we have that VDS issues also. So there are some systematic errors. So what is the voltage which is generated here because of this particular circuit? If I plot it here, okay, so it is around 500. Okay, so that is the Baising voltage, and on top of that I have this AC signal. On top of that I have this AC signal. Okay, so this is how I have done use the current mirror and given the generated this DC operating voltage for this transistor, and also I have used a constant current source out here. Now this is 1 millivolt, and if I take V out, okay, let me cut all the unwanted signals.
Sir, can you just keep the schematic for some time?
Yeah, okay. Yeah, tell me.
I was not able to follow. You just, from the right side to left side. I mean, where you have used a current reference is like a R3 resistor,
here,
right?
Yeah.
There you generating the current.
No,
okay, that is the
this current I have taken already. Assumed that this current is available 20 micro.
Yeah, this is the reference current.
Yes.
Right.
Yes.
So from M3 transistor, you have a diode connected. You coming back to the M2 transistor.
Correct.
Right. That is the bias voltage.
Correct.
On the left side, M4 is your common source amplifier. Right.
Correct.
If I'm not wrong.
Correct.
And this R2 is coming again gate to the M5 transistor.
Yes.
Directly.
Yes. That is that
and
is
again,
VB which we have generated.
Sorry.
VB bias voltage.
Are you generating the bias voltage for the, okay, you generating some different voltage here, right?
Yes. Yes.
This M5 transistor can be outside for some outside purpose, something else. Maybe
Yes,
you can consider as a VB as a label.
Yes, VB. Yeah.
This R2 is acting as a breaker between the C1 and the M5 capacitance.
Yes,
if I'm not wrong.
Correct.
Okay. Because picture is coming towards left side, reference current to the it is taking some time to understand.
Okay, I have drawn the reference current on the right hand side.
Okay.
Is this okay with all of you? Anybody else has got some doubt? Right now, if I do it and if I measure the output current, it is 30 millivolt, right, from peak to peak. Instead of 1, I am getting 30. Okay, that is because I have instead of RD, I have used an transistor out here. Okay, instead of RD, I have used a constant current source which has got much higher resistances. Okay, so that is the reason the gain now if you see it is more than 25. So I am getting much better results out here, right? Now what is the drawback of this particular circuit? I cannot connect a low load out here, right? Now if I replace this by say just 100 ohms, if I run it, right, so it has gone into micro, right, 400 micro, so the gain is disappeared, so I can't have. So in case I want to drive a low load, so I have to modify this circuit, and I have to probably put this output voltage drive another CD amplifier or a source follower, right? So that is what is done out here. So now this voltage which I am generating here, okay, I am using it to bias this transistor. Okay, so if I do that, then I don't have, so there is a DC operating point here, right? So that DC operating point in the initial circuit, it was 0.5 volt only. So that was not good enough. I found that is not good enough for this circuit. So I wanted to increase it further. So how do I increase it further? By changing again the W/L ratios of these two transistors. So if I do that, I am getting the desired DC voltage, operating voltage here. So that DC operating voltage is sufficient to drive this particular transistor. Now if you see in this particular the load is only 100 ohms. So in spite of connecting a low load out here, if I take the voltage output, so I'll get a good like 10 millivolt to 10 millivolt, right? So obviously from here to here there will be some drop, Okay, so the unity gain, so some drop, but still earlier if I connect this 100 here, I was getting only microvolts, right? But I am connecting it here, microvolt. I am getting
it is too
10.
fast.
Sir, can you show the schematic?
Yeah, see.
So sir, here M2 is biased in a linear region.
No, M2.
It has to be it should work as a resistor, right?
Yes, it is not in linear region. 1.2, 1.6 volt is the voltage available, right?
Yes. So when we are biasing it in the saturation region, we are implementing it as a current source.
Yeah, current source only.
Okay. And sir, one more thing. When we are connecting 100 ohms at the common drain output, how much power it is taking from the V3?
It will take. It will take. This will consume more power. Let me.
Can you sir just plot that?
Let me plot the powers. Power consumed by this transistor, it is around it is varying from 220 to 480 microwatt. Okay, whereas here it is just you will find here. Okay, so this is the power which is being consumed by this. This is the power which is consumed by this transistor. Is it okay?
Okay. Yes, sir. Yes, sir.
Okay. So these are the kind of circuits which you can design. So whatever theory what we studied, if you try to implement in LT Spice, then you will find there will be some variations between the theoretical values what we calculated, right? Because of these are BISIM 3 models, so it takes into consideration various short channel and narrow width effects also. So they are close to real transistors, the models which I have supplied you. So you will find from the theoretical first order equations what we are using, there will be some variations. Okay, so